Hello everyone, welcome to lesson 1.6, a library of parent functions, day 2. Today we're going to talk about two different types of functions. We're going to talk about step functions and piecewise functions. A common step function we're going to look at today is called the greatest integer function, and it's given as f of x is equal to, and then they have this interesting symbol. It's like a bracket with an extra line in it, x, and then it closes off with the same kind of bracket. What we read that as is, this is the greatest integer that's less than or equal to x. Just to help you understand what that means, say we have this greatest integer symbol and call x -1. We're really asking, what's the biggest number that is less than or equal to -1? And in this case, it's going to just be -1. Sometimes that might be a fraction. Like, what if we have the greatest integer of, say, -1/2? We're looking for the greatest integer that's less than or equal to -1/2. In this case, the closest integer is -1. Let's look at a couple other ones. What if we had the greatest integer of 1/10? Here we're asking what number is less than or equal to 1/10, the biggest integer, and in this case that's 0. This can also be used with decimal problems. Say we've got 1.5. The greatest integer, the number that's less than or equal to 1.5, would be 1. And also we could look at 1.9. So we're looking for the greatest integer number that's less than or equal to 1.9, and in this case that is 1. There are some characteristics of this greatest integer problem we need to look at. So we're going to look at the characteristics of f of x is equal to the greatest integer of x. Some characteristics of this function are that the domain of the function is the set of all real numbers, and the range of the function is the set of all integers. So it's not all real numbers. So remember, real numbers include decimals and fractions. Integers do not. So we, for our domain, can use decimals and fractions, but no matter what we use for x, our f of x, our y value, is always going to be an integer. It can never be a decimal or a fraction. Another characteristic of this function is that the graph has a y-intercept at 0, 0, at the origin, and it has x-intercepts in the interval from close bracket 0 to 1 parentheses. So that, remember, that means we include 0 and everything between 0 and 1, but 1, if we were looking at a graph, would be an open circle. Another characteristic is the graph is constant between each pair of consecutive integer values of x. And the last characteristic I need you to know is that the graph jumps vertically 1 unit at each integer value of x. So let's actually look at an example of this greatest integer function, which is a step function. So we are going to evaluate the function f of x is equal to the greatest integer of x plus 1 at a few different x values. So we're going to do this when x is equal to -1, when x is equal to 2, and when x is equal to 3 over 2. So first, let's find f of -1. All we're going to do is we're going to take the greatest integer of -1 and then add 1 to it. Remember from the last little page I had, the greatest integer of -1 is the number that is less than or equal to 1. That's -1. That's an integer. So we've got -1, and then we're going to add 1 to it. So in this case, f of -1 is going to end up being -1 plus 1, which equals 0. That's pretty nice. Let's also look at when the function when x equals 2. So f of 2. That's going to be the greatest integer of 2 plus 1. And in this case, the biggest integer value that is less than or equal to 2 is 2. And then we add 1 to it. So the function when x is equal to 2 is going to be 3. Pretty nifty. Let's then also figure out that last x value, 3/2. So f of 3/2. As a reminder, that's about like 1.5. So we're looking for the greatest integer of 3/2. So the greatest value that is less than or equal to 3/2, that is an integer, and then add 1 to that. Since 3 over 2 is equal to 1.5, exactly, the greatest integer close to but smaller than 3/2 is 1. And then we add 1 to that, and we're going to find that f of 3/2 is equal to 2. So that's not too scary, I hope, for you, evaluating a step function. Oh, and I forgot to mention, this is example number 2 for when you're doing your post-video check. And the final example we're going to look at in lesson 1.6 is example 3, which is graphing a piecewise function. Which I know you did talk about piecewise functions a while ago in this class. But anyway, the piecewise function we are going to graph, and you're going to see the screen change to graph paper soon, is we are going to graph f of x is equal to 2x plus 3 when x is less than or equal to 1, and negative x plus 4 when x is greater than 1. So I'm going to switch the screen to some graph paper. Alright, so I'm going to quick draw in my x and my y axis. I'm going to utilize this space to make and graph this piecewise function. So, if we remember from Algebra 2, how we can graph these two equations, we've got 2x plus 3. There's two important things we should make note of. One of those is this 3 value. Remember, that's our y-intercept. 2 is our slope. So let's just start by graphing this equation and not worry about the constraint of x is less than or equal to 1. Okay? So if we're graphing this, what we're going to do is we're going to start at the origin and we're going to go up 3 units to our y-intercept and we're going to put a point there. From there we can utilize our slope. Our slope tells us we have to go up 2 y units and over 1x unit. Now I could keep going, but I don't want to go off my graph. So I could also go down 2 y units and left an x unit. And I can repeat that pattern until I have enough to connect my dots and make a line. Now I'm going to come back at the end once I get both of them graphed and erase some things. Okay? So let's now look at graphing our negative x plus 4. So here our y-intercept is at 4. So we're going to go put a dot on our graph at 4. And our slope is a negative 1. That means we're going to go down 1 y unit and right 1x. And we can keep doing that till we have enough dots to make a line. Now what I'm going to do in my graphing process is I'm going to go back and I'm going to erase some parts that I don't really need. Okay? So in my red line, my condition is that x is less than or equal to 1. So I don't need my graph to go past the x value. So really, in the case with this graph, I'm just going to erase the arrow where my x would be 1. In my blue line, my condition is that x is less than or greater than 1. So I'm going to erase all the parts of my line where x is less than 1. Which means I'm going to erase everything to the left of 1. I might have to come back and fill back in some of my red line. And one other thing to note, what's going to tell me the end behavior of these lines is that inequality symbol. If we have something that does not have a line underneath it, like our second condition, instead of putting a dot where x would be 1, we're going to put a circle there. With our red line, we have the line underneath the inequality symbol, so we want to keep our dot there. If there was no line there, we would erase the dot and we would replace it with a circle. We've erased the parts we don't need for this function, so we are now done graphing this piecewise function. Pretty neat. Alright, so finally there is one other part that I'm not going to put on this video. I want you to see page 64 in your textbook, and I want you to copy the graphs of parent functions into your notebook. There's about 8 graphs, and I don't need them to look perfect. I just want you to have a rough sketch of what these different types of graphs look like. Some of them we did include in this video and the last one. This concludes our lesson on 1.6. Next lesson will be 1.7. I'll see you in class.